Welcome back. In this last block on dimension reduction, we're going to talk about factor analysis. And this section is actually a little bit longer than the other ones, partly because factor analysis is fairly common in the social sciences, or especially was fairly common in the 70s, 80s, 90s. It has gone a bit out of fashion, and this is kind of striking with a lot of these methods, multidimensional scaling, factor analysis, and related techniques. They were very fashionable in the 80s, 90s in both political science and in economics. They have been sort of taken over by other econometric techniques as regression models improved and were better able to deal with latent variables that we cannot observe or categorical variables that we cannot use linear regression. These techniques sort of got out of fashion, in part because they don't have the same kind of measures of uncertainty and standard errors, etc., that we are used to from econometric techniques. So these econometric techniques are good for inference from a sample to a population, better than these methods are. But these methods are still very interesting methods to summarize data, to reduce the complexity of the data, to visualize data, etc. And now with the trend of data science and machine learning, these techniques are somehow coming back in the social sciences from a different route. So there's a kind of a funny scenario where they were considered old-fashioned in econometric analysis. They have been disappearing from the social sciences, and now they are considered fashionable because they are techniques used in computer science and data science, and that is considered advanced and is now coming back into political science and social sciences. It shows a bit how data science is really not as new as people suggest it is. So factor analysis is a third dimension reduction technique, and it's really fairly closely connected to principal component analysis, but somewhat different, and slightly different priorities and a slightly different modeling strategy. So again, we have a set of a high dimensional space, say defined by words, where we can position documents, or by documents where we can position words, but it can also be, for example, a psychological test with a lot of questions related to how you behave. You might have done some personality tests, for example, where you are introvert versus extrovert, and judging versus observing, etc. So when you do these tests, you answer a lot of questions, and then the computer somehow from these many questions derives how you might score on a few of those latent traits that we cannot directly observe. And that's what factor analysis also does. It's one of the techniques that are used in those kind of contexts. So we are looking for latent variables, for underlying dimensions that describe much of the data that we see, even if it's not as detailed. So you can imagine that we saw already with principal component analysis that you might have many dimensions, but that most of the variation is really along 1 or 2 or 3 dimensions. And so factor analysis is based on the same idea and then tries to model those. But the underlying modeling is a little bit different, and it finds these underlying dimensions. We are also going to see that we talk about scores and loadings exactly like we talk about those in principal components analysis. In fact, I think that terminology is primarily from the factor analysis literature. And in some cases, under some circumstances, for example, when the variance in all the observed variables is very similar, then factor analysis will really lead to the same result, more or less, as principal component analysis. But in other cases, it will be a little bit different. So the idea is to find these underlying latent traits, these underlying dimensions of the data. So we can use it, for example, on the economic data. We have 5 different variables that all measure something about economic development. We want to reduce that to fewer dimensions so that we can visualize it. We can't make a plot with 5 axes. So we do a factor analysis. We obtain scores, we obtain loadings. On the left, you see the scores. On the right, you see the loadings. Now, you might at first sight think that the left is totally different from the principal components, but then if you look a little bit longer, you see that actually they might be similar. Factor 1 looks a bit like dimension 1, where we had Croatia, Romania, Italy, Australia, Netherlands, all on the left. That was the same in principal components. Benin, Malawi, Cambodia, they were all on the right on the first principal component. They're also all on the right for the first factor. So really the main change is that factor 2 is flipped. North The low values and the high values, they have flipped sign. That is not really a big change. So the picture that we see on the left is really quite similar to the principal component analysis, a little bit different. But the main difference is really that it's a mirror image of the other. And also on the right, where we see which variables are more closely related to each other, which ones are more further apart, it's a little bit of a similar image. Similar, but a little bit different. Now, one thing that we always talk about when we talk about factor analysis is rotation. So with principal component analysis, there's a very clear rotation of these axes. The first axis is the one that describes the most variation, exactly. The second axis is the second most variation, exactly. So there's a fixed kind of rotation. Factor analysis does not work like that. Factor analysis tries to reduce from many factors to fewer. You have to always specify how many factors you're looking for. It will reduce to these fewer dimensions, and it will define a space defined by these fewer dimensions, but there is no clear definition of how the axes are drawn. So for example, here we might obtain the solid line axis as the factor 1 being the horizontal axis and factor 2 being the vertical axis, and the points being the data points. But really, if we had rotated it in this two-dimensional space, and we get the dashed lines, for example, or we get the dotted lines, the points would not have changed, right? So the point pattern is exactly the same. The scores will be different for each observation, but the points haven't actually moved, right? So for example, we can talk about this observation here, and without rotating, it would score this on the first factor and this point on the second factor, right? That's the location of that point. But then after rotation, let's take a different color. To go for the dotted line, we could say it also might have this location here and this location on the dashed axis, right? So the locations, the factor scores will have changed. Yeah? So the factor score here is different from the factor score here. But the actual point hasn't moved as such, right? How these points relate to each other has not moved. Which points are close to each other, which ones are far apart, and how far apart has not changed at all. So within this reduced dimensional space, within this space of only 2 dimensions, we can still rotate the axes without changing our description of the data as such. Just the coordinates of each point change, but not how the points relate to each other. And so that means we have a number of options for rotation. In this case, I'm talking about orthogonal rotation. That means that the 2 lines are perpendicular to each other, and they stay perpendicular to each other. Yeah? Now, there's different ways of rotating. Usually, we try to find a rotation so that for each of the factors, some variables correlate strongly and other variables correlate weakly with that factor. So if all factors correlate somewhat with all variables, it is very difficult to know what these factors might represent, what they might mean. But if some factors correlate strongly with some variables and other factors correlate strongly with other variables, then we can look up what these variables are, and from that conclude a little bit what these factors might mean. Yeah? So for example, when we do this psychological test and we ask a lot of questions on behavioral questions or preference questions, then maybe some of these dimensions, they relate to this introvert versus extrovert. And if we can rotate the factors so that they strongly correlate with some variables and weakly correlate with other variables, then maybe we find a factor that strongly correlates with all the variables that have something to do with extroversion and introversion, and weakly correlates with other questions in the same test. So that way we can try to find out what these factors mean. It's always a post hoc interpretation. There's no clear definition of what they mean. And there's no input by the researcher what they mean. But we can look at the factor loadings. So the loadings are the correlation between the variables and the factors to see what they mean. One very common rotation is varimax, which is an orthogonal rotation, just like we saw in the previous picture. Oblimin is the one that is most common when we do not necessarily want to assume that they are orthogonal. Yeah, so we can also rotate in a way that they're not the same anymore. So for example, if here we look at the red lines, let's see how this works. So we already had, for example, for this point that it scores here on one factor and here on the other factor. And then we can rotate the factors. And if we allow for this orthogonal, non-orthogonal rotation, then you end up with one that has a position on one axis here and one on another position here. Yeah? So this was a straight angle, but this is not at all a straight angle. Yeah? So we allow correlated factors, and sometimes that can help for interpretation. So here's an example of a very much rotation. So we have the same data on the left that we showed before, but we have rotated a little bit. Remember that Romania and Croatia were here and they have moved this way. Yeah, I should draw that rather. So Croatia and Romania, they were somewhere here and they moved here, yeah, through the rotation. Malawi was somewhere here and moved there, right? So everything is rotated a bit. Rotated in a way that we can more clearly interpret the factors. And in fact, when you look on the right and we look at the factor loadings, which is, you see indeed that for factor 1, these variables all score high on factor 1, and these all score very low on factor 1. So factor 1 now much more clearly separates these two factors. So factor 1 is now about growth rate, fertility rate and mortality rate, and factor 2 is a little bit less. Yeah, so you can see the correlation. Now, unfortunately, here we see that these are high on both factors and these are low on both factors. So it doesn't work. It's not an ideal rotation, but you see the idea. And we can also just describe it. So we can do a factor analysis on this economic data. We can say that we want to extract two factors, and then we can either apply no rotation or apply very much rotation. Yeah, so we see here the data. So we say that we want two factors, and then we can choose which variation we want, which rotation we want. So without rotation, you see that these are all very strong correlations, and these are all kind of moderate weak. So it's difficult to interpret what this factor might mean. After rotation, you see somewhat more stronger rotation correlations here and a strong correlation here. So this changes a bit how we interpret it. On the left, you can say factor 1 captures sort of everything and factor 2 nothing really. But on the right, we can see that factor 1 captures life expectancy, infant mortality, fertility rates, and GDP, whereas factor 2 is really about growth rate. And also, to some extent, perhaps, these two. It's not an ideal example. Like usually you hope that they separate more clearly. Yeah, so here there's a lot of overlap between the two factors, and it's kind of difficult to interpret them. I will give an example in a moment where the results were a bit more satisfactory. Yeah, so with Oberlin, with correlated factors rotation, we get a somewhat different result. And the picture really starts to look quite different from what we saw in the PCA. Yeah, so the underlying dimensions in factor analysis are called factors. And when we look at the data points on each of the factors, we talk about scores. And when we talk about the variables on each of the factors, we talk about loadings. We can also do that, for example, with the term document. So when we have a data set, a document term matrix, then the rows, the observations are each the speeches. The variables are the words. And the data is the number of times this word is used in the speech. Then the scores would be for the underlying dimensions, how each word is related, or each speech is related to each factor, and the loadings would be how each term is related to each of the factors. And if you know how each term is related to each of the factors, that will tell you something about the substantive meaning, right? If you know which words score high and which words score low, you might understand what the underlying meaning is of that dimension. Here's a totally different example from some applied research that I did a few years ago. So in 2008, we had a referendum in Ireland on the Lisbon Treaty on European integration. And there were quite a few different items mentioned in the campaigns, by the different campaigns. So these were all statements by the yes and the no campaigns about what was in the treaty. So they would say, if you vote yes, we lose the Irish commissioner. If you vote yes, you will be forced to be, they will introduce conscription to a European army. If you vote yes, then Ireland will not be able to maintain its anti-abortion policy at the time. So these were all statements that were made. And then some of them are clearly in the treaty and some of them are clearly not in the treaty. The treaty did not speak of a European army. And the abortion policy was really not part of the treaty. Now, you could argue that if you integrate further, you lose a bit neutrality. And you could argue that there was some statements on workers' rights. So these are a little bit ambiguous. But most of the statements that were made, they were quite clearly either correct or really not so correct. And they were emphasized by different campaigns. The no campaign emphasized those points. The yes campaign emphasized those points. Now, what we wanted to do is to see whether, when we ask each of those, I think it's 11 of them, to respondents in a survey, like, do you agree that this was part of the treaty that we are voting on, can we find any sort of underlying trends? So we ask everybody, yes or no, is this part of the treaty? Respondents gave an answer to that. And then we did a factor analysis. And then we apply very max rotation because we wanted to make sure that some of these variables will strongly correlate with one factor and weakly with others weakly, and with the other factor then a different distinction. And you see on the right that this kind of works. So you can see the factor loadings there. So for factor 1, the loadings are on the left. For factor 2, they're on the right. And the rule of thumb normally is that if a factor is stronger than 0.4 or less than minus 0.4, we consider that a relevant loading. So these in bold are the factor loadings for these variables with factor 1, and you can see that some of them have strong and other ones have weak correlations. And here these have strong correlations and these have weak correlations. And so what we found interesting and what our paper is about is that these two factors really separate the two campaigns. So this is really the no campaign scores, and these really capture the yes campaign scores. Except for the loss of Irish commissioner, where the two really did not distinguish. So we were able to conclude something about how the perceptions by voters of what is in the treaty was strongly influenced by one or the other campaign. Yeah? So people tended to either follow the yes campaign or follow the no campaign, regardless of what was correct and what was wrong. Yeah? So it's not that they separated people that understood the treaty and people that did not understand the treaty. It really separated people that followed the yes campaign and people that did not follow the yes campaign. So this is an example where the rotation works better, where we could really separate these two groups and we could really write a paper around these findings in factor analysis. So principal component analysis and factor analysis, they're closely related to each other, but they have some sort of slightly different key features. Yeah? So principal component analysis models all the variation in the data. You get as many factors as that you get, as many dimensions, components as that you have original dimensions in the data. Yeah? So it models all the variation. But the first of those components will capture the most variation it can, the second, the most variation that is left, etc. So by looking only at the first components, you capture a lot of the data. But the actual solution to the PCA has all the dimensions. Factor analysis, on the other hand, is always a reduction to fewer factors, which tries to separate the variation in the data that is common, that we can capture by some underlying dimensions, and variation that is unique to individual variables. So it separates the common from the unique variation in the data. And it captures these common variations through underlying latent variables, to underlying factors, and then models the unique variation for each variable. A little bit technicality, but that's what happened. The PCA, one is a summarizing method, so it summarizes all the data, and it's good for description of the data to understand where most of the variation is. Factor analysis is always designed more with the perspective of a model. Can we model latent variables, underlying dimensions that describe this data? So one is, PCA is used more commonly for visualization or for reducing the complexity of the data before we continue with other methods. Factor analysis is more used as a model to try to understand the data, to interpret the data, for example, in psychological tests. PCA, it does not matter how many dimensions you extract. In fact, the solution is always to extract all of them, and then you might look at the first few. Factor analysis, if you extract a different number of factors, and you always have to specify how many you do, the results will be different. So the first factor will not look the same if you extract 2 compared to when you extract 3 factors. In PCA, it does not matter how many factors you extract. The first one will always capture the most variation in the data. And so it will always be in one particular shape, defined by definition. PCA preserves the distances, the variation, I should actually say, preserves as much of the variation in the data. I think that is more appropriate. Yeah, so it preserves the variation, whereas factor analysis tries to preserve correlations in the data. It tries to find a common variation, which has to do with covariation. PCA has an exact analytical solution, so it's clearly defined what the principal component is, and you can calculate it exactly. Factor analysis is an approximation. It uses some kind of search algorithm to try to find an optimal solution for these factors. And so different methods are available, and they will lead to slightly different results. PCA, this is really a technicality I don't want to delve into here. So one is within the space, each subset of components defines a subspace of the original space in which the variables are located. Factor analysis actually adds axes that are beyond the space in which the variables are observed. PCA has no particular underlying assumptions about the data. It is just a mathematically defined summary of the matrix. Factor analysis has somewhat stronger assumptions. In fact, it assumes that the data has a normal distribution. So it really should be used only for continuous variables that have a normal distribution and that also jointly have a normal distribution. I have to admit that here, this is of course not the case. These were binary variables. People said yes or no to each of those, and then we applied factor analysis. So this analysis was a nice result, but it's a slight violation of the underlying assumptions. Yeah. So here there is in the literature some discussion whether there's a major difference between confirmatory versus exploratory factor analysis. I'm not going to delve too much into that debate. This really goes back to the way factor analysis was used more commonly in the 70s, 80s, 90s, and how it is much less used now. Yeah, so now PCA is commonly used all the time as part, usually on an intermediate step in an analysis, to reduce the complexity of the data before we continue with the analysis, or to visualize complex data to somehow get it into a two-dimensional space that we can view. Factor analysis is in fact now really used a little bit less, primarily within the sort of design of tests and surveys where we look for underlying dimensions. It is heavily criticized. Factor analysis is heavily criticized. All right, and people argue that it can either be used for two ways. So we can either argue that there is some underlying variable. We can argue that there is such a thing as introversion versus extrovert, or judging versus observing, etc. And we can then design a test that captures these and perform a factor analysis to see whether indeed these variables that we think all capture the same thing also correlate with each other with the same factor, have high loadings on the same factor in the factor analysis. So here the idea is that before the factor analysis, we say these are the latent factors we expect to find, we perform the factor analysis, and we see to what extent it does. The alternative is to use it to explore the data, to use the data to find, so do we find factors or not? And especially the latter is really heavily criticized. You want to be a little bit careful not to draw too strong conclusions from what you find. We are in this course, in data science, it is really used more as exploratory data analysis, but the substantive conclusions are usually weaker than we try to do in social sciences. So we have a number of dimension reduction techniques. If you want to preserve correlations and you are trying to model latent traits or latent factors, latent features of this data, factor analysis is the common method. If you want to have a lower dimensional representation for visualization, for example, and you are primarily concerned about preserving the distances, variables that are far apart in the high dimensional space should stay far apart in the low dimensional space, multidimensional scaling is the method to go for. If you want to reduce the number of dimensions, for example, to produce a plot, and you want to preserve as much variation in the data as possible, so that we preserve as much of the information in the data as possible, then PCA is the way to go. And there are close relations between factor analysis, PCA, and MDS. To some extent, given certain assumptions, they do the same thing. So you can specify under what assumptions MDS means PCA, and under what circumstances factor analysis is really the PCA solution as well. And that's it. Thank you.